Hi guys, welcome back to Am I Audible? First of all, okay. So welcome back to the tutorial series on basics of quantum computing. So let's start with the recap. So last day we looked at an algorithm which was the DOSH algorithm, and the purpose of the algorithm was to find if we are given an unknown function f, whether that function is constant or balanced. So constant meaning f0 and f1 are same, and balanced meaning they are unequal. And we saw that if we wanted to solve this problem classically, we had to choose an oracle which is a black box which represents the function, the unknown function f, and we will have to make two queries to the classical oracle in order to find whether it is constant or balanced. But with the help of quantum mechanics and with the help of this quantum circuit, we were able to show that with only one query to the oracle, you can actually find out if the function is constant or balanced. And so basically, with the help of the quantum algorithm, we obtained a speedup. And the phenomena which led to this speed up, which we concluded were parallelism and phase kickback. And both of these were enabled by the phenomenon of quantum superposition. So this upper superposition, Kate plus, which we fed to the first qubit, allowed us to calculate F0 and F1 at the same time. And the Kate minus, which we input to the second qubit, actually helped us to uh, convey the information of F0 or F0 in terms of a phase. And that helped us to finally conclude if the given function, the unknown function, was balanced or constant just using one query. Okay. And although we have looked at this very simple algorithm, uh, uh, you can also have, there are other quantum algorithms. So we have the Dosh-Jozsa algorithm, which is just a generalization of this algorithm to more number of qubits. And you have Grover search algorithm, quantum Fourier transform, Shor's factoring algorithm. And all these algorithms give you can solve the problem faster than their classical uh, counterpart. And just like here, it was able to solve in less number of steps. So basically, in these algorithms also, you can show that in less number of steps, the corresponding the problem can be solved compared to the corresponding classical algorithms. Okay. So far, so on this, on the Deutsch algorithm part, do you guys have any questions or queries? Karthik is asking, कि with the current quantum computer, can we implement this algorithms or qubits are not sufficient? Well, yes, you can implement these algorithms with the help of current quantum computers. Uh, but the thing is that in order to, so basically, let's say if you let's consider this Dosh-Jozsa algorithm, for example. So uh, this grows if you see classically this algorithm, the complexity grows as 2 to the power n. So if n is the number of bits. And from the quantum solution, you can show that with a constant number of steps, you can solve it. But now the question is that with the current number of qubits that we have, or rather good qubits that we have, can we have can we do something which would be impossible to do with the classical algorithm, like the best classical supercomputers cannot do, but my quantum computer can do. So if you're asking that, then yes, the number of qubits is not enough. So if we make n very large, then there's a lot of noise and decoherence setting in, and yes, you cannot really uh, get any advantage out of it. So basically, and another thing is that our qubits are noisy, so there are a lot of errors, and we need something called quantum error correction in order to deal with that. So the basic idea of quantum error correction is that you take say some number of physical qubits. Let's say you take 6 physical qubits, or let's say 7 physical qubits. And using this 7 physical qubits, like these are the actual atoms or superconducting qubits, the actual physical objects. And in the 7 physical qubits, you encode only one logical qubit. So this is something that we need to do, the process of quantum error correction, in order to implement these algorithms without errors. So suppose if you look at the Shor's algorithm, then in order to get say advantage over uh, any classical algorithm, you need at least say I think around 100 logical qubits. And with the current the best surface codes and all these things that we have, 100 or even more, let's say 1,000 logical qubits will give us a good advantage over classical algorithms. And then if you have to have 1,000 logical qubits, then with the best surface codes, you would need 1 million physical qubits. And that is something we do not have yet. So I think the best ones are of the order of 500 or so, if I'm not wrong. Does that answer your question? Okay. Anything else? Any other queries from the last session's stuff? So whatever we did on Deutsch algorithm, or any other general questions like. Yeah, we need to wait, and basically, hopefully, in a in at most a decade. So in say the next 10 years, we will uh, hopefully have something which will have these many qubits. Okay, so if there are no other questions, then let's go ahead with uh, today's discussions. So today, let's revisit the problem of measurement. So let's say we have some kit psi, and suppose this can be written as alpha phi naught plus beta phi 1, where phi naught and phi 1 form an orthonormal basis. And we had seen previously that if you measure this psi in phi naught phi 1 basis, what you have is that you get the probability of getting, say, get phi naught was simply you took the projection along phi naught of psi and the mod squared of that. So basically, this was like kind of analogous to like this n dot v whole square. So basically, the projection of v along n. So here the inner product does the same thing. It takes the projection of. So if I just take, let's say, phi naught psi, then we had the projection of psi along phi naught. So this is what we had, and of course, this would be nothing but mod alpha squared. And in a similar sense, you can say that probability of phi 1 will be nothing but the projection along phi 1. Okay, and mod squared. Now, so basically what's happening is that you have this measurement apparatus, which is measuring along the basis phi naught, phi 1, let's say, and you have this initial state psi, and here with some probability, with alpha squared probability, you are getting phi naught, and with beta squared. So this is all everything which we already know, nothing new. Now, now the question is, suppose I have, in this case, I have inputted psi, and after the measurement, I have got phi naught. So can I express the measurement by some operator? So the question is, can you replace this by an operator? And so basically, can you do the following? So let's say get psi, and then instead of this measurement device, I'll put an operator P naught, and can that give me some phi naught? So can I find such a P naught? Okay. So basically, so what I'm asking is, I need P naught acting on psi to be get phi naught. And psi we have already defined here as alpha phi naught plus beta phi 1. So let's write that. Let's substitute that value of psi here. So here you have alpha get phi naught plus beta get phi 1. So can you guess what this P naught operator can be? If I want to get phi naught from here. So phi naught by alpha. Hmm. So you're saying that P naught, so P naught has to be an operator, right? So if it is just phi naught by alpha, then pra phi naught. Okay, so you're saying that pra phi naught by alpha. Is this what you are saying? Kate into pra. Okay, good. So yeah, so if you uh, use this, like P naught, if you set this, then you will get phi naught. So basically, uh, here, if you have phi naught by alpha, acting on this alpha phi naught plus beta phi 1, that's right. So you would get this. So this is my operator, which would uh, like give me a phi naught from psi. So remember, this is my state psi. All right. So turns out we don't call this entire operator P naught, but instead we just call the part phi naught, phi naught. So phi naught we call P naught. Okay. So and this is the this is called a projection operator. Because you see, this is what it is doing is that it's taking the projection of so if you just apply this P naught operator, let's like okay, so let's let me call this P naught dashed P naught dashed. So P naught dashed is a ket phi outer product by alpha, which is an operator. Now we are taking this P naught, okay, which is the projection operator. Sorry, this is operator. Yeah. So if I take P naught on psi, just this part without the alpha, then what will I get is I'll just simply get so let's phi naught, and this is acting on this. So here you would have phi naught, and then so alpha, the first term will be alpha phi naught, and then phi naught inner product plus beta, and you have again phi naught here and phi naught phi 1 inner product, and so this will be 0 and this will be 1, and you're just finding alpha phi naught. So basically it gives us the projection, or this is nothing but the vector projection of psi along phi naught. So that's why these operators are known as this operator is known as the projection operator. Now, yeah, and as like already Anmol has mentioned that it will be P naught by alpha acting on psi, which will give me phi naught. Now, let's try to find out alpha. But you see, alpha is a variable. So let's try to make this as a function of, write this as a function of P naught and psi. Okay. Okay. So if we have this from here, we can also write that if I take the dagger on both sides, then ket phi naught will become bra phi naught. And here we will have something like P naught dagger by alpha star bra side. So I have taken dagger on both sides. So basically conjugate and transpose on both sides. Now, if you look at this P naught operator, um, so this is, it looks like phi naught outer product. So let's use this. Now, if you take P naught dagger here, what will happen? So the order, so remember, this outer product is nothing but, so this is a column vector, this is a row vector. So the order will change and each one will get dagger. So phi naught will, this grade one will come first, but if you take the dagger of bra, you will get kete. So you get phi naught. So basically, let me write it out. So we get this and then get phi naught dagger. So bra phi naught dagger will give you get phi naught, and get phi naught dagger will give you bra. Maintain this, so bra phi naught. And you can see that P naught dagger is nothing but T naught. Okay, so basically I can also write from here that phi naught is P naught by alpha star psi. Or rather, I'm sorry, yeah, this order will also be changed. So P naught dagger by alpha star. Yeah, because you see, this is again a matrix multiplication, and on taking the dagger, the order changes. So this operator will act on the bra vector from the brackets. Okay. Now, if we alpha also you can represent right like this. Okay, get phi naught psi, because you see this nothing. This gives you when we took the projection while calculating the probabilities. For example, let's say here. So here, get phi naught psi was nothing but alpha. So alpha can be written like this. And here, this would be, so we found that P naught dagger is P naught, so just P naught. So phi naught, we will replace by psi P naught and psi by alpha star. So here we get alpha star mod alpha squared is this quantity. And mod alpha would be root of get psi P naught psi. So basically, if we write alpha equal to mod alpha e to the power I theta, because here we have from this calculation we have got mod alpha, but we do not know the phase that alpha has. So if we P naught psi, and we would have a e to the power I theta here. So we can take it to the other side. So we can write this. This whole thing acting on side will give you e to the power I theta get phi naught. But you see, this is a global phase and it can be ignored. Okay, so basically on if I have this get psi, and if I do a measurement in the basis of phi naught and phi 1, then I would get either P naught by this into psi, or I would get P1 acting on this. Okay, and the probabilities would be and with the corresponding probabilities, which will again be given by the projections themselves. So basically, okay. So when we are measuring, either P naught by this will act on psi, or P1 by this will act on psi. Okay, and P naught and P1 are said to be the projection operators. All right, and they together define something. Now, let us look at some properties of this projection of matrix. Um, so one thing which you can see is that if I apply, say, P naught, so let's say P naught is this phi naught outer product. If we do P naught squared, so basically P naught into P naught, then what will we get? So here we'll have phi naught from the first P naught, and then again phi naught from the second P naught. And again, what this within the red circle. This is the inner product of phi naught with. So get back. So if I put 1 here, we get back phi naught. A beauty of the bracket notation also, like it simplifies your calculations so much. And phi naught is again your P naught. Okay. So this is one property that we have seen. P naught squared is P naught, and similarly you can show that P1 squared is P1. And the other, so what does this mean physically? This means that if, let's say, you are basically measuring psi, and suppose so P naught will act with some probability, and let's say P naught acts, and P naught by that factor, whatever, and then you get phi naught. If you again act P naught on it again, it will not change. Okay. So like it will be equivalent to the like operating P naught once and operating P naught twice are equivalent. Okay, that's the physical significance of this property. And the other thing that you'll notice is that if you take the sum of these two operators, then it would be something like this. And you can, let's say I take phi naught to be some general state. So in C2, I am taking phi naught to be. So it would be something like this, as we have seen before. You can write a general state in the Hilbert space of a qubit, which is C2, like this. And phi 1, let's say, is the orthogonal vector to phi naught, so it would be something like this. And if you put phi naught and phi 1, you can figure out that if you substitute these two things here, then you would find that P naught plus P1 equal to I. And the significance is that phi naught, so this ensures that phi naught and phi 1 are the only possibilities when we do this particular measurement. Okay. So that's the physical significance, and you can also write this as phi naught plus phi 1 equal to identity. So these are the general properties. So you see, we have seen three properties of this operator. First is that P0 plus P1 we saw is identity, and then also P naught squared equal to P naught and P1 squared equal to P1. And also we had seen that here P naught dagger equal to P naught, and similarly you can show P1 dagger equal to P1, which means that P naught and P1 are partition. So Now with that, let's try to describe projection operators more generally. So, or the projective measurement more generally. So any general projective measurement can be described by the projection operators. P naught, P1, and up to PA. Okay, such that so the projection operator should follow the following criteria, that P naught should be Hermitian. In other words, P naught dagger should be, so, or for a general PI, let's say. So PI dagger should be equal to PI. And then this summation over all PIs should give me identity. And also PI squared should be equal to PI for all I. And this is also for all I. So if there is a set of operators P1 to Pn which satisfy these three properties, then they can describe a projective measurement. Okay. Now, if you say, let's say I am writing the projector corresponding to kits, so that will be outer product 0. Okay. Now, is kit 0, is this projector kit 0, this operator, is it unitary? Can you guys check if it is unitary or not? So in order to check whether it is unitary, you just have to do, you have to check if these, if you take this, whether that is identity. Okay, so Anmol says that it is not unitary, but Rajrupa says that, like Rajrupa says yes. So do you mean that it is unitary, or uh, do you mean that it is not unitary? Okay, so the answer is that this is PWP, yeah, not unitary, right? So yeah, you can just write it in the matrix form, and you would see that P0 dagger P is not identity. So this is not unitary. Okay, but you see, we had said that all evolution in quantum mechanics should be unitary. So, but but when we are measuring, we are applying some operator which is not unitary. So, Can you guess why that is the case? Like what I'm saying is that we have said that quantum evolution should be unitary. So that was our postulate. But here in measurement, we are applying operators which are not unitary. So length of projection is not the same as the length of original abstract vector. Yeah, that is the mathematical answer, but I'm saying that, yeah, that's why it is not unitary. So the norm is not getting preserved, although you can like add the, just divide by this normalization factor. So this normalization factor you can divide it by, and you can again get back the same norm. But um, but does it not violate the like the fact that measurement is not unitary? Does it not violate this postulate that quantum evolution should be unitary? Any ideas? So, am I actually telling you correctly that quantum evolution always has to be unitary? So, remember, was there any constraint on this statement? Was there something else in this statement? So the thing is that quantum evolution is unitary only when the system is closed. So quantum evolution of closed system, that would be unitary. But here, when we do a measurement, then the system interacts with the measurement apparatus. So if the system is interacting with the measurement apparatus, it is no longer unitary. So if the system, so when we are measuring, the system interacts with the measuring apparatus. Or in other words, during the measurement, the system becomes open. Okay. So the evolution of a open system may not be unitary. Okay. And this is the evolution in the open system is not unitary. Is that clear? So that's why measurement, so when we are measuring, the system is not remaining closed anymore and it is becoming open, and that's why the projection operators which describe the measurement are not unitary. So is this thing clear? Yes, no, anything? So if you guys have any doubts, you can ask. Okay. So if it is clear, then let's try to understand it in an even better way. So what is the, so let's try to see what is the projection operator doing, let's say the P0 operator doing on the block sphere. So if we have this projection operator P0, get 0, 0, and remember that on the block sphere, so block sphere was the representation in, was a real space representation of the complex vectors in C2, and it turned out that the ket0 was represented on the z-axis and the ket1 on the minus z-axis, because these were eigenvectors of the sigma z operator or the sz operator, you can say. So if you, so what does this P0 do? So let's say I have some initial state here. It will ultimately take it to ket0. Okay. Now if I have something here, even then it will take it to ket0. So this operator P0, P ket0 does not perform a, like cause a fixed rotation on the block sphere. Which means that it does not always rotate the block vector about the same axis, about by the same angle. So remember, when we had unitary operations on the qubit, they caused some rotations on the block sphere, and they caused some rotations about some fixed axis in roof by some fixed angle chi. But here you say it is rotating by pi by 2 about some axis. This is now some, sorry, this is some other angle about some other axis. So P0 does not cause a fixed rotation on the box. And we said that unitaries will cause a fixed rotation. So it will cause the rotation about by some definite angle about some definite axis. Okay. So P0 does not do that. And from there also you can see, like from this visualization also you can understand that the projection operators P0 is not unitary. So in general, we can say, and as I mentioned, that measurement, when we are doing some measurement, then the system becomes open. So measurement um, is a non-unitary process. So is this clear? So from the block sphere, how you can understand? And it is for this reason we have a separate postulate for measurement and collapse. And we cannot incorporate it within the measurement postulate. Now, okay, if this is clear, then let's move on. So now let's ask the question, is it not a rotation then? No, it is not a rotation. No? As you have seen that it is not rotating by a fixed amount. Yeah, like at the end of the day, it is some rotation, but it is not a fixed rotation. Okay, so because if like in even in measurement, if I input a pure state, like a normalized state vector, I will get a normalized state vector. But the thing is that it is, the rotation is not fixed. Okay. And just give me a minute, the tab has disconnected. So is this clear? Okay, this is some rotation, of course, but this is not a fixed rotation. So P0 does not rotate by a fixed angle about a fixed axis. So is that clear, Rajrupa? Uh, is it an arbitrary rotation by some angle? Yeah, it is an arbitrary rotation, Elias. Yes. It is an arbitrary rotation by some angle, by some about some axis, and what rotation will take place, that is again dependent on the what state you are measuring. Okay. And also, like when you are doing the measurement, like P0 will act with some probability, P1 can also act. So from this point, for example, from this point, it can go to gate 0 or it can go to gate 1. If P0 is acted, it will go to gate 0. If P1 is acted, it will go to gate 1. Okay, so this is how you can visualize the thing. All right, so now the reason moving on to the like so here we have taken, you see, a measurement in some basis. So we have said okay, measurement in some kit plus kit minus basis, and or some phi naught phi 1 basis, and we have constructed projection operators corresponding to them. But now the question is that how is it related to the concept of observables? Because in quantum mechanics, we know we are measuring some observables actually. So even when we are saying that we are measuring in some basis, we are actually measuring observables. Measuring some observable, let's say M. Then how is this M observable, which will has to be a Hermitian, of course, in order to have real eigenvalues. So how is this connected to our, this projection operators? So let's try to see that. So let's say we have this measurement operator M00, 01, 10, M11, and this is this is defined on C2. Okay, defined on the complex place C2. Now, if you have this operator, then you can also write it as M00, let's say get 0, get 0. So if it is written in the 01 basis, okay, then M00 will be get 0 outer product, M01 will be get 1 outer product. Okay, so you can write it in the in terms of this basis. Now, let's say this measurement operator has some eigenvalues lambda 1, lambda 2. So if the eigenvalues are lambda 1, lambda 2, then on measurement, we will get either lambda 1 or lambda 2. Okay. And let's say the corresponding, these are the eigenvalues. And let's say the corresponding eigenvectors are something like get E1, get E2. These are the eigenvectors. All right. So if this is the case, then you can show that M can also be written as this. It can be written as lambda 1 get E1 get E1 plus lambda 2 get E2 get E2 out of product. So basically, you see, previously we were defining it in this 00011011 basis, and now we are defining it in a new basis, which is get E1 E1 get E2. So get E1 get E1 get E2 get E2. That is the basis corresponding to the eigenvectors. So if you write it in a so of course this get E1 outer product is the projection operator corresponding to E1, and this is the projection operator corresponding to E2, Kt2, Kt2 output. But if I can also write it in again in a matrix form, which is lambda 1, lambda 2, where the matrix is now expressed in some other basis. So E1, E2, E1, E2. So basically, this is exactly what you do when you diagonalize a matrix. So you go from one basis to another basis. Okay. So you just do a change of basis when you are diagonalizing a matrix. So what we are saying is in the basis of the eigenvectors, the matrix M will be diagonal, and it can be written in the form where eigen value times the projection corresponding to the eigenvector plus the another eigenvalue and projection corresponding to that eigenvector. Okay, so in order to understand this, let's look at an example. So let's say we have SZ. So SZ is an observable. So is this Z component of the spin angular momentum that we had seen, and it is like h cross by 2 sigma z. So sigma z will be 0, 1, 0, minus. And this is in 0, 1, 0, 1 basis. Okay. Now, this is already diagonal, so you can just simply write it as h cross by 2, h0, get 0, minus h cross by 2, get 1, get 1. So you see, h cross by 2 is the eigenvalue corresponding to 0, and minus h cross by 2 is the eigenvalue corresponding to 1. So basically, we have written it in this form, lambda 1 p1 plus lambda 2 p2. Okay, so you can write any operator in this form, and this is how the operators and projectors, like the Hermitian operators corresponding to observables and the projections corresponding to the measurements, projective measurements, are related. And let's say if we had Sx h cross by 2 sigma x, then it would be like h cross by 2 0, 1, 1, 0. But if you so here this is again in 0, 1, 0, 1 basis. So in this basis, this would be like ket 1, ket 0 outer product plus h cross by 2, ket 0, ket 1 outer. But if I know that what the eigenvalues and eigenvectors are, so I can write it in another form also. So the eigenvalues are plus h cross by 2 and minus h cross. Corresponding to plus h cross by 2, I know that sigma x has the eigenvector get plus, so I'll just write get plus minus h cross by 2, get minus, get minus. Okay, and if you calculate this, this will again give you the same matrix in 0, 1 basis. And if you want to write this matrix in plus minus basis, then this would be like this. Plus, get minus, get plus, get minus. So is this part clear? Any questions, queries till here? So, one thing, if there's nothing, I would like to briefly mention one thing, that this representation is not only valid for some Hermitian matrix or any other spatial matrix. If you take any matrix, you can decompose it like this, and this is known as the spectral decomposition. like writing a matrix in terms of its eigenvalues and eigenvectors. So you have the lambda 1, lambda 2 here, and the outer product of the eigenvectors here. So why is it for spectral decomposition? Because the eigenvalues and eigenvectors are referred to as the spectral properties of a matrix or a linear operator in general. Okay, so if there are no questions, then let me go on to the main topic for today, which is density matrix, and which are also known as density operators. And in order to understand density matrix or density operators, we first have to understand what an ensemble is, or I don't know the correct pronunciation. Some people also say ensemble. So whatever is fine for you. So, so what is an ensemble? So an ensemble is a large number of copies of a system. So let's try to understand this with the help of an example. Okay. So let's say I have a black box here, black box, and this is this gives some quantum state uh, as an output. Okay. And I am running this black box again and again and trying to see what output it is giving. So let's say I run it in the first run. Uh, I run the black box, so it's abbreviated by BB, and then I get say get phi naught. Second run, again I run the black box, again I get phi naught, and like this I run it a large number. So where n is very large, I run this black box and I always get phi naught. So see this, so I have got a large number of copies of the same system, right? So this is known as an ensemble. And we see here that the output of the black box is always get phi naught. And so if this is the case that the black box always gives me the same output, then the system is, so the system here, so we want to ask you what is the state of the system here. So we would say that the system is in a pure state. Okay. And well, yeah, so basically, since it is a pure state, you can describe it by just the state vector phi naught, or you can write a density matrix for phi naught. So if there's a pure state phi naught like this, the density matrix would be outer product of phi naught, phi naught. Okay. So let's take an example and try to understand this. So let's say if I have phi naught is say get plus, so basically get 0 plus get 1 by root 2. So in the matrix column vector form, it would be 1 by root 2, 1 by root 2. And so the raw vector would be the row vector 1 by root 2, 1 by root 2. So simply the transpose, because conjugate does not change anything. And if you find the row like this, then now we take the outer product. So basically 1 by root 2, 1 by root 2, and 1 by root 2, 1 by root 2. So the density matrix corresponding to get phi naught, we will find is so half, 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 half. So this will be the density matrix corresponding to the pure state phi naught. So this is how we define the density matrix. Just the outer product of the state with itself. Okay. So for a pure state, we can say that outer product of state with itself. Now, let's take a different ensemble, let's say. So basically, again, I have a different black box now, and let's try to see what that outputs. So now, in this case, let's say I am running the black box again and again as before, but now sometimes I am getting phi naught, sometimes I am getting phi 1, let's say. Okay. So in some of the cases, I have given received phi 1, and if I have run n times, then let's say n by 2 times, the black box gives us get phi naught, and n by 2 times, it gives us get phi 1. Okay. But so if I have done this experiment n times, then if I have to predict what it will output in the n plus 1th time if I run the black box, it will give phi naught, get phi naught with 50% probability and get phi 1 with 50% probability. Is that okay? Now, uh, in such a case where and I want to know what is the state of the system. So sometimes, so it's not, I can't describe it. It is clear that I cannot say that it is in ket phi naught, or I cannot say that it is in ket phi 1. Okay. So 50% of the times it is in phi naught, 50% of the times it is in phi 1. Okay. So the state of the system here, I will say that it is a mixed state. Okay. And I will describe it by a density matrix, which is rho. So basically, half of the times it is in rho ket phi, phi naught. Sorry, let me. And half of the times it is in rho ket phi 1. So I would describe it like this. So basically, I would take the density matrix corresponding to the pure state phi naught, density matrix corresponding to pure state phi 1, and combine them according to the probabilities with which it is present. For example, phi naught was present with half probability, so half plus half rho get phi 1. And of course, this you can, as we had defined just a while ago, this you can write as phi naught outer product plus half, this you can write as phi 1 outer product. Okay. So this is how you would describe. So again, this is an ensemble, and in the ensemble, sometimes it is phi 1, phi naught, sometimes it is phi 1. That's why we have to now use a mixed state in order to describe the state of the system, and we would do it like this. So is this part clear to everybody? Any questions? Yeah, so basically so that's a very good question. What is the difference between projection operator and density matrix? So for a pure state, there is no difference, because you see, for a pure state, I can, so this is nothing but P phi naught. Okay. So for a pure state, the density matrix and the projection operators are the same. But when we are taking a mixed state, then this is no longer this object, which is like half row phi naught plus half row phi 1. This is not any projector operator. Is that clear? And yeah, you are absolutely right that for a pure state, the density matrix is the projection operator. Okay. Is that clear? Okay. Now, so if you have understood this, then let me okay, then let's okay. So this thing, what I have described here, is exactly equivalent to also saying that I have a box, let's say, where I have a lot of qubits, and some of them are in, say, K0 state, some of them are in K1 state. So let's say the blue ones are all K0 states, so some are K0, and there are some which are K1. Okay. And if I choose any one system and try to look at its state, then it will be exactly similar situation. So basically here it is necessary that we don't know which qubit is in, or let's say it can be any qubit system, let's say electron, photon, anything. So each qubit is in which state. So the exact, so we know that some of them are in zero, some of them are in one. And although I'm marking that, okay, these are in zero, these are in one, we actually don't know that which qubit is in which state. But we know that 50% of them are in Ket zero state and 50% of them are in Ket one state. And you can see that this is exactly equivalent to this scenario, this black box scenario. In this black box also, if we took any run of the black box, the output could be either phi 0 or phi 1. Okay. And here also, if we choose any particular qubit from this ensemble of qubits, then it would be either Ket 0 or Ket 1 with 50-50 probability. So if I choose one qubit from this box, the state of the qubit will be given by the density matrix, which would be half probability it would be Ket0 outer product, with half probability it will be Ket1 outer. Is this okay? So do you guys agree that these two situations are equivalent, exactly equivalent? Okay. So then let me ask you the following question. Okay, let's say you have, so we were working with quantum circuits before, and let's say we have a general n-qubit quantum circuit, okay, and I have done measurements on the qubits at the very end, and when I have done the measurements, uh, half of the times I have gotten 0 and half of the times I have gotten 1. So if I choose any qubit randomly from this, then randomly, I'm choosing it randomly, but when I choose, I know that I am choosing the first qubit or second qubit or third qubit. So let's say I choose the third qubit. Then is the state of the third qubit is the state uh, rho equal to this 0 0 plus 1 1 by sorry, wait. Uh, I hope this is visible. Yeah. So this is the question. So what do you guys think? Any ideas? Like you can take a guess. Just take a guess. Anything. Yes, no, any random guess. Just after measurement, mixed state becomes a pure state. Okay, so so the answer is it yes or no? Then no, right. So the reason the answer is no is because although here, see, these two situations seem very similar. Yeah, yeah, it is possible that you get 0 70% time and 130% time. In that case, the probabilities will be different. The probabilities will be 7 by 10 and 3 by 10. So let's say here, okay, let me first answer that question. So if you have, say, 30% of the time, 30% one get one and 70% get zero. So if this is your ensemble, then the row will be 7 by 10 uh, get 0 plus 3 by 10 get 1. Okay. So yes, it is possible. And now to answer this question, whether the state here is a mixed state, it is no. Now you see that these two cases are very similar. Here also there is 50% Ket 0 here and 50% Ket 1. And here also we have 50% Ket 0, sorry. 50% Ket 0 and 50% Ket 1. But then what is the difference? Here we know exactly, since we have measured, we know exactly which qubits are in which state. So the reason it is no is because we know that which qubit is in which state. We know exactly. But in this case, we know that 50% are Ket 0 and 50% are Ket 1, but we don't know which of these qubits are in Ket 0 and which of these are in Ket 1. So basically, we get a mixed state because of our ignorance, because we don't know. And so this is something which is called the subjective ignorance. Okay. So is this part clear? See why we have a mixed state here and why we have a pure state here? So for example, in this case, if I chose, say, the second qubit I have measured and I have seen that it is in Ket 1. Okay. So the state of the second qubit will be Ket 1, not 0 0 plus 1 1 by root 2. Okay. Sorry, not root 2, 0 0 plus 1 1 by 2. But here, if I choose any one system, then I don't know which ones are in 0 and 1, right? So here, because of our ignorance, because of the ignorance of the subject, we have a mixed state like this. Is this clear? So let's now contrast it with objective ignorance. So when we had a superposition states, let's say 1 by root 2 0 plus 1 by root 2 1. Here it is not, we don't know whether I will get 0 or 1 on measurement, but this is not due to my ignorance. In this case, even the object, which is the quantum state itself, does not know whether it is in ket 0 or ket 1. So object itself does not know if it is in ket 0 or ket 1. So that's why this is known as objective ignorance. So in quantum superposition, we have objective ignorance. But when we have a mixture of quantum states, we have what we call subjective ignorance. So is this part clear? Is this concept of subjective objective ignorance clear? And why we are taking density matrix, this concept of ensembles. If there is any questions, let me know. Subjective ignorance. Okay, I'll repeat another time. So, see, I have a box which has 50% Ket 0, 50%, I have with say 100 qubits, 50 of them are in Ket 0 and 50 of them are in Ket 1. Okay, but I do not know which qubit is in Ket 0 and which qubit is in Ket 1. Let's say I choose this qubit, okay, this qubit. So I do not know whether it is in Ket 0 or in Ket 1. And if you think about it, this is a situation which arises a lot of times in classical statistical mechanics. For example, when we look at, say, an ensemble of gaseous molecules, we do not know exactly which molecule is moving with which velocity. But we know what is the average velocity, we might be able to know what is the mean squared velocity, and so on and so on. But the exact whether it is whether that gas molecule is moving with exactly v velocity or v1 velocity, that we don't. So in a similar way, when we are choosing so we have a collection of electrons in the box and we don't know which electrons is in which state, then it is my ignorance. So basically, I don't know whether it is in 0 or 1. And that's why I am getting a mixed state like this. Okay. So basically, the fact that I don't know is reflected in the quantum state, in the state of the particle. Okay. So this is subjective ignorance. And as I said, objective ignorance again, here it is not my fault that I don't know whether it is 0 or 1. But if it is in a superposition, then the object itself does not know whether it is in 0 or 1. So now is the concept of subjective and objective ignorance clear? Yes, exactly. So the subjective ignorance corresponds to classical probability. Or you can say that for a mixed state like this, where there is subjective ignorance, this can be reproduced by, like, can be, these statistics can be reproduced by classical mechanics. But the statistics of this state cannot be reproduced by classical mechanics. And this is something which is very interesting. While objective ignorance is quantum, yeah, you can say some, yeah, exactly. So when you have objective ignorance, it is, you can say that it's a quantum superposition. But if there is subjective ignorance, then it's in a mixed state, that you can say. Yes. So let me try to elaborate it in the to like tell you the difference in this fashion. Okay. So we again have some Ket zeros and Ket ones, and again we have this subjective ignorance of that we don't know which is in Ket zero and which is in Ket one. Okay, and here I have another box where each qubit or each electron or whatever is in this superposition 0 plus 1 by each and every one of them. Okay, all are these green ones. So here, if you choose one qubit from here, and if you try to tell its state, because of subjective ignorance, you would get 0 0 plus 1 1 5. Sorry, 5. And here, since there is no there cannot be any subjective ignorance because every one of them is in 0 plus 1 by root 2. So if I have to write the state here, I would just write 0 plus 1 by root 2. Or if I have to write in density matrix, I would just uh, find out the density matrix corresponding to psi. Yeah, so is this difference between the mixed state of 0 and 1 and the quantum superposition of 0 and 1, is this clear? So if there is any questions, again, let me know. So initially this might be a little bit confusing. So if you are having questions, then that's okay. But do speak up if you have any questions. Okay, so I'm assuming that there are no more questions. So let's try to subjective case. Okay, the denominator can be anything. No. Array, see, this corresponds to the probabilities. Half 0 0 plus half 1. So this is like the probability that it is in 0 and the probability that it is in 1. Like basically what fraction of this ensemble is in 0 and what fraction is in 1. Okay. So um, yeah, so let's so that since you have asked that question, let's define the density matrix in a more formal way. So if we have a system is a statistical ensemble of pure states psi 0, psi 1, and psi n with probabilities p0, p1 up to pn. Then the state is rho. So it would be like P0, psi 0 plus P1, psi 1, psi 1, and so on up to Pn, psi n, psi n. Okay, and if you just compare with this, then you see that this half is nothing but P0 and this half is nothing but P1. And there are only two terms here. Okay, so and also we have to make sure that, so we can write this as Pi psi I, and you have to make sure that summation Pi is 1. Okay, so the denominator cannot be anything. The coefficients of 0, 0 and 1, 1 has to be such that they add up to 1. Okay, so that's formally how you would define a density matrix. Okay, now, so is it clear? Okay, so now let's let's try to see how we can, what the Born rule becomes. So Born rule was nothing but the whatever we discussed in the beginning of the class. So basically, uh, this is what the Born rule says for a pure state at least. Okay, so yeah, so for a pure state, we had this. So it told us the probabilities of getting different outcomes. Okay. So yeah, it said the probability of getting, if we measure phi naught, it's just the projection of psi along phi mod squared and so on and so forth. So this is something which we have already seen. Now the question is, what will this Born rule, the rule that gives us the probability of getting some outcome on doing a measurement, what will that be? So so for mixed state, mm, so or rather for a density matrix, so density matrix can represent both pure and mixed state. Okay, for a density matrix, what will the Born rule be? So it turns out that if you have a certain row, if the system is in a certain row and you are measuring in get phi naught, get phi 1 basis, okay, then the probability that after measurement you get phi naught, or the like the eigenvalue corresponding to get phi naught, is just trace of rho, the projection operator corresponding to phi naught. So basically trace of rho, sorry, uh, phi naught, phi naught outer product. And similarly, so I'll define what is a trace, don't worry. Probability of phi 1 is trace of rho p phi 1. And again, the projector is just phi 1 outer product. So it's like this. Now, what is trace? So a trace of a matrix is just the sum of its diagonal elements. All right. So, and if you and this will be your homework to that if you put rho equal to some pure state, let's say psi psi, then the probability, then, and if you put it back in this equation, then you can check that you will recover the Born rule for the pure states, which is just phi 1 psi whole square. So you can just check that this is consistent with whatever we had done before. Okay. So now, so is this any questions here? Okay, if not, now let's see what the total probability will be in this case. So in the case of pure states, or let me say for state vectors, which represented only pure states, the total probability we had seen was represented by the norm of psi whole squared, and we had set it to 1. Now let's see what it would be in case of test dimension. So you see, the total probability will be just the probability of getting phi naught plus probability of getting phi 1, right? So total probability of getting phi naught plus probability of getting get phi 1. And here we have seen that probability of getting get phi naught is this trace of rho p phi naught. And probability of getting this is trace of rho p, sorry, phi 1. And trace is a linear operator, so you can, so trace of a plus trace of b is nothing but trace of a plus b. So you can write this. And you see rho will be common here. So, and here we have p phi naught. Now, this we had seen when we were looking at the properties of projectors, that since phi naught and phi 1 are the only possibilities, the projector corresponding to phi naught and projector corresponding to phi 1, if you add them, then this turns out to be identity. So this is something we had seen just a while ago. Uh, so So yeah, here we had seen that P naught plus P1 was identity, and also in the general definition, summation Pi was identity. Okay. So from there we can put that it is just, so P phi naught plus P phi 1 we can substitute by identity. And so trace of rho times I, and rho times I is of course rho. So trace of rho gives you the total probability. Okay. And just like in the case of state vectors, we had put the total probability equal to 1. So here also we will put total probability equal to 1. All right. So any questions so far? Okay, then let's uh, look at something else. So let's take a density matrix like this: rho 0 0, rho 0 1, rho 1 0, rho 1 1, which is again defined on the Hilbert space C2. And so of course this is in the 0, 1 basis. And you can, if you diagonalize it, so basically you can write it in a spectral decomposition form also, as we had discussed for the Hermitian operators. So basically you can write it as P naught, uh, E naught, E naught plus P1, E1, E1, where the P naught and P1 are eigenvalues, and with the corresponding eigenvectors E naught, E1. Okay, so basically, again, this is equivalent to diagonalizing the matrix, taking it to the basis of the eigenvectors of the operator. Sorry. Now you see E naught will be some pure state, so will be the density matrix corresponding to some pure state. So basically I can write it as P naught rho E naught plus P1 rho E1. So basically it is clear that P naught and P1 are some probabilities. These are probabilities. So it's just the probability that P0 is the probability that of getting E0 on measuring, and P1 is the probability of getting E1 on measuring. Okay, so these are probabilities. So, and these probabilities are nothing but the eigenvalues. Okay, so probabilities have to be real, so eigenvalues have to be real. So let's see, probabilities have to be real. Which means that eigenvalues has to be real. Which means that rho has to be Hermitian. Also see that probabilities have to be non-negative. So probability can be 0 or positive. So P0, P1 can be greater than or equal to 0. And P0, P1 are again the eigenvalues of rho, remember? So we can say that eigenvalues have to be non-negative. Okay, and that means that rho has to be positive semi-definite. So if a matrix has non-negative eigenvalues, it is said to be positive semi-definite. Sorry. Or sometimes it is just represented by rho greater than equal to 0. Okay. All right. So these are some of the properties that the density matrix is having. So let's write them down in one go. So properties of density matrix. So one thing that we saw from the fact that the probabilities have to be real, from that constraint, we found out that rho has to be Hermitian. So this is the first property. Okay, and from the fact that the probabilities are non-negative, we found out that rho has to be positive semi-definite, or in other words, its eigenvalues have to be non-negative. Okay. And the third property that we had found out from the fact that total probability is 1 is that trace of rho is 1. So you see, all these properties arise very naturally, very logically they arise. Right? So Hermitian arises from the fact that probabilities have to be real. Uh, Positive semi-definite arises from the fact that probabilities have to be non-negative, and trace of rho equal to 1, that arises from the fact that total probability has to be 1. So these are the properties. So any questions still here? Semi-definite means, okay. So semi-definite, uh, semi-definite means eigenvalues are greater than 0. Okay. So positive semi-definite would mean this. Okay. Oh, sorry, positive definite would mean this. And what positive semi-definite means? This means that eigenvalues are greater than or equal to, that is semi-definite and definite difference. So definite means that it is definitely greater than 0. Semi-definite means that it is okay, it can be greater than 0 or it can be equal to 0 as well. Okay, so that's what semi-definite means. Okay. Okay. Uh, all right. So now, what is very important is that we want to write in the qubit case, in the case of a qubit, that is when the Hilbert space is C2, how can we represent rho? And this is a very important question. This will probably the most important thing that we will learn in this course. Represent rho, a general density matrix. This representation is very important. So, if you want to represent rho, we first have to look at the properties of rho. Okay, so what are the properties? First property is that rho has to be Hermitian. So let's look at the set of all, and since this is rho on C2, so that these density matrices are all 2 by 2 matrices, right? So let's look at the set of all 2 by 2 Hermitian matrices. Okay, because we have said that the rho has to be Hermitian, so rho will belong to this set, the set of all 2 by 2 Hermitian matrices. Now, you can show that this forms a vector space over the field of real numbers. This is very interesting because you see, Hermitian matrices are actually complex matrices. So the individual elements of the Hermitian matrix are complex, but it forms a vector space over real. So you can check all the conditions that I had given you in, I think, session 2 in our tutorial 2. You can check all the conditions for vector spaces and you would see that all these conditions would be met. So for the time being, let's look in detail at the closure conditions. So let's say M1 and M2 are Hermitian. Let's say. Okay. And let's take M3, which is some alpha M1 plus beta M2. So so M1 and M2 are Hermitian, what does that mean? That means M1 dagger is equal to M1 and M2 dagger equal to M2, right? That is the meaning of Hermitian. Now let's try to see if M3 is also Hermitian or not. So first let's assume that alpha and beta can be complex. Let's say that they can be complex, okay? And let's take the dagger on both sides. So this would be alpha star M1 dagger plus beta star M2 dagger. And since M1 dagger is M1 and M2 dagger is M2, you would say that alpha star M1 plus beta star M2. And so if M3 has to be Hermitian, then you see M3 dagger has to be equal to M3. But in M3 we have alpha M1 plus beta M2, and here we have alpha star M1 plus beta star M2. So in general, they won't be equal. M3 will not be a Hermitian unless alpha and beta are real. So if alpha, beta are real, then of course alpha star is alpha and beta star is beta. And you have M3 dagger, which is alpha M1 plus beta M2. And that is nothing but M3. So we have M3 dagger equal to M3. Okay. And that means if the scalars multiplying them are real and the scalars come from the field, so scalars come from real numbers, then uh, this linear combination of M1 and M2 will be closed. So the vector space would be closed under multiplication and addition or under linear combination. Okay. So uh, M3 is Hermitian if and only if alpha and beta are real. Okay. Now, if it is like Hermitian, so basically if rho is Hermitian, then it will belong to this vector space, the space of all 2 by 2 Hermitian matrices on R. Okay. Now, one important basis of this, so there can be an infinite number of bases of this Hilbert space, but one important basis is identity, sigma x, sigma y, and sigma z. So basically, identity and the Pauli matrices, they form a basis of this space of Hermitian matrices, because you see they themselves are Hermitian. And if you multiply them by some real number, they will again be Hermitian. Okay. So any Hermitian matrix we can write as a linear combination of these four matrices. So, and we know that our density matrix in the property we have seen that because the probabilities have to be real, rho has to be Hermitian. So rho is a Hermitian matrix, and we can write it as some linear combination. Let's say T I plus some U sigma x plus V sigma y plus W sigma z. Okay, so we can write it where, and since this is like vector space on the field of real numbers, this T, U, V, W are all real. So T, U, V, W are real numbers. Okay. So this is how you can represent a density matrix. But wait, we have only imposed the condition that rho is Hermitian. Okay, but there are other two conditions also. So one is that trace of rho 1. So let's apply this condition that trace of rho has to be 1. Okay, so if trace of rho is 1, then what will we have? So trace of Ti plus U sigma X plus V sigma Y plus W sigma Z. This is 1. And again, as trace is linear, we can just say that T times trace of identity plus U times trace of sigma X plus V times trace of sigma Y plus W times trace of sigma Z. This would be 1. And so we have to calculate trace of sigma X, trace of sigma Y, trace of sigma Z, and trace of Y. So for polymatrices, you already know what the polymatrices are. I'll leave you to you guys to check that trace of sigma X, sigma Y, and sigma Z are all 0. Okay, so basically that's why polymatrices are traceless. So since this trace is 0, we say that they are traceless. And trace of I, what is that? So trace of identity is just 1001, and trace, you remember, is just the sum of diagonal elements. So diagonal elements are what? 1 and 1. So 1 plus 1 is 2. So trace of identity is 2, and all the rest of these terms are 0. So this is 0, this is 0, this is 0, and trace of identity is 2. So we are left with 2t equal to 1, because on the right hand side we had 1 because trace of rho equal to 1. So we get t equal to half. Right. So let's substitute t equal to half here. What will we get? We will get half identity plus u sigma x plus v sigma y plus w sigma z. All right. Now, there's only one condition which we are left to apply, is that it is positive semi-definite. Where did it go? Uh, yeah, so rho has to be positive semi-definite, or in other words, the eigenvalues are greater than or equal to 0. All right. So if you write this row in a matrix form, you would get. So I'll just tell you the results right now. You can check at home. So half plus W, half minus W, U minus IV, and U plus IV. So let's, if you try to calculate the eigenvalues, lambdas of rho, then you will get these two eigenvalues. So one would be half plus root over of u squared plus v squared plus w squared, and half minus root over of u squared plus v squared plus w squared. So how we are getting this is your homework. So you can try to calculate this. It's not very difficult, it's quite straightforward. You just have to find the characteristic equation. So basically lambda I minus rho equal to 0, and from there it will be a quadratic equation. You just have to apply Sridharacharyya's formula or the quadratic formula to get this. Okay, and the this is of course greater than 0 by default. Now this can be like with proper values of u v w, it can be either greater than 0 or less than 0, or it can be 0. But remember positive semi-definiteness. So which said eigenvalues have to be non-negative. That means this eigenvalue, which is half minus root over of u squared plus v squared plus w squared, has to be greater than equal to 0. Okay, and if you solve this, then you would get u squared plus v squared plus w squared less than equal to 1. Okay, so let's now do a little bit of a mathematical jugglery, a little transformation. So let's define U as x by 2, V as y by 2, and W as z by 2. Okay. If we do that, then you will see that this is x squared plus 4 plus y squared by 4 plus z squared by 4. That is less than equal to 1. That means x squared plus y squared plus z squared is less than equal to 1. Okay. So basically, finally, we can write that rho can be written as this. Where did it go? So rho can be written as this, where your u squared plus v squared plus w squared is less than equal to 1. Or you can just replace u by x by 2, in which case, and v by y by 2, w by z by 2, in which case you would get x by 2 sigma x plus y by 2 sigma y plus z by 2 sigma z. So basically, I plus x sigma x plus y sigma y plus z sigma z by 2, where x and y and z cannot be just anything. They have to follow this constraint that x squared plus z squared plus 1 is less than equal to 1. And if you write our vector as x hat, so just bear with me. I know it's past time, but just this is the last line. So sigma, if we write as sigma x roof plus sigma y roof plus sigma z roof, then we can write rho as I plus, you see, x sigma x plus y sigma y plus z sigma z is nothing but r dot sigma. Okay, so I plus r dot sigma 2, and x squared plus y squared plus z squared is nothing but mod r squared. So this tells us that mod r squared equal less than equal to 1. That means mod r should be less than equal to 1. So we can write that mod r is less than equal to 1. Okay, so it was a pretty long calculation, but the summary is that if you apply these constraints that rho has to be Hermitian, positive, semi-definite, and trace of rho equal to 1. If you apply all these constraints, then you can express the rho in this form. At least for a single qubit, you can express rho in this form. And this is going to be very important. So I would ask you guys to think about the significance of this representation. Okay. So this, please think about this. And if you have any questions, tell me. Yes, exactly. You're right. So that is what we will discuss in next class. You can actually represent rho in block sphere. Okay. Yeah, that's the right answer. Okay. the significance is that you can represent rho in block sphere. And I would encourage you to think how that would be possible. And if you come up with a scheme, I would ask you to um, like check if all the known points, all the points that you know on the block sphere, okay, the um, z-axis points, okay. Uh, so the z-axis points will be ket0, ket1, the x-axis points will be ket plus, ket minus. So please try to check that and try to think how this representation would help us represent rho on the block sphere. Okay, so any other questions? Well, I expected a lot of questions because this is something which is completely new that we have introduced. Uh, okay, if you don't have any other questions, so please go back and try to go through these calculations. I have jumped a lot of steps here. So mainly here, where I have just written down the eigenvalues for you. Please try to calculate them by yourselves. And okay, so I'll be here for a couple more minutes in case if you have any doubts. Or even if you want to discuss something else, it's fine. Is any operator can be represented in this form? No, only the density operator. So, or any operator which follows these constraints, they can be represented in this form. So basically these three constraints. So if you have any operator which uh, like satisfies these three constraints, only then you can write rho in this form. Okay. So yeah, by the way, this is the second last class. So the next class will be our last. So we will finish up density matrices and talk about partial trace in the next class. Okay, so I think there are no more questions. Uh, so we will let you know the timings of the next class via email. And okay, so bye. Thank you for attending. Thank you for your time. Okay.